Right. Today I'll start some how to Fermions acquire the mass by the Yukawa interactions in the standard model. The content from the particle physics written by the Thompsons, as already we much shown in the previous videos, like the spontaneous material breakings and the X mechanism and standard model. And in the previous videos, we already see that the spontaneous matrix breakings as choosing some specific vacuums, and it will make some symmetry breakings of the Lagrangians in the potentials, and it will make the some massive field by the non-zero spectrum expectation values, and the second reaches there will be the interaction between the particles and the scalar fields. And we already see that some examples of the real scalar fields, U1 symmetry complex scalar fields, and the U1 gauge bosons, and the ST2 gauge boson as a TWS model in the previous several videos. And today, there will be some couplings between the fermion, such as spinors, and some scalar fields, such as Higgs, and it will give some fermion mass, like the Quark and the electrons. And reminds that we show that some gauge symmetry, some local gauge invariance video reminds that there are some Dirac mass terms, things like that. And if we expand this sort of the right-handed and left-handed at the color side, then there will be some mixing term of the left and the right-handed sides. So it is not color symmetry. So in the standard model, we choose satisfy that the such left-handed color symmetry of the SC2, but the such Dirac mass terms does not give the color symmetry of the standard model. So such a Dirac mass term should be removed. So there are zero mass. And there are some similar problems in the gauge boson mass that we shown in the local gauge invariance video. So let's consider such as Yukawa interactions, for example, as a locked-on case. So there's a left-handed double last and the right-handed single last, and a double last scalar piece. So we can expand this as a matrix form. There will be some left-handed double last, which has components of neutrino and electrons. There will be the Higgs double last, which is the charged Higgs and the neutral Higgs, and there are right and singular and Hermes combinations. And there will be the interactions, coupling constants for the Yukawa interaction. These Yukawa interactions and Yukawa interaction forms is a spinor as joint spinors, colors and the spinor. Sometimes it is written by the pi size as psi on the psi. And such as interaction terms is imbalance under the SAT color symmetry times U1 symmetry in the standard model. The such interaction will give that the non-zero mass of the fermions. So we will choose the non-zero vacuum expectation values and the small perturbation of the Higgs fields in the neutral color phase component. And it will give that such interaction terms. Interaction between the electrons and the Higgs field, and the non-zero vacuum expectation values gives that the electron mass. The electron mass is determined by such a vacuum expectation values and the coupling constants of the Yukawa interactions, and there will be also Higgs electron couplings as a triple Betsax, which is the coupling constant, it depends on the mass of the electrons and the vacuum expectation value. So such a formalism is also applied for the D-typed cake. For example, there are different coupling constants CD for the different mass of the D Kirk, and the Kirk double last are the left-handed, and the double last 6 and the right-handed singular and Hermitian conjugate, and it gives a non-zero master of the decay and interaction between the DKX and the Higgs, and such a master of the DKX are determined by the spectrum expectation values and the coupling constant. And we want to apply the similar formalism for uptype cake, but the problems is the developed like that, pi plus pi zeros for the scalar. Developed and there are u and d. So and the only non-zero vacuum expectation is only in the neutral scalar component, but is only coupled to the d-type cakes and the Baudelaire case electrons. But there are no coupling for the type cakes and the neutrino. So we defined the charge conjugate with of the scalar developed, which is convert of the neutral scalars and the charge scalars and the components, such as complex scalar with components that given like that, like the pi 1, pi 2, pi 7, pi 4. And there's a non-zero expectation values and the X appears in the upper part. And if we expanded this, then the expanded of these Yukawa couplings between the left-handed Higgs last and the charge conjugates of the Higgs colors last, and it gives that also master of the Quark and the interaction between the Higgs and the Higgs beam. And I want to mention about there are some Quark mixing because the Blyver's eigenstars and mass eigenstars are different. So in general, there are some generations of the Quark. We show that there are some of the up-type Quark and down-type Quark, which is the electric charge is 2 over 3 E and the minus 1 over 3 respectively. And there are generations of this such up and down-type Quark. So there are chums, twins, and top and bottom. And we can give the index for that each generations as I and j, we see equal to the 1 and 3. So for example, U1 is just a U, and U2 is just a C, and U3 is equal to the T. So there are some such generations for the left and the right hand is developed singular respectively, and we can give the some Yukawa matrix which is of diagonal terms. So there will be some mixing between the such as terms. So U and S, U and B, C and D, and things such as mixing will be appears in the diagonal terms in Yukawa matrix. And if we diagonalize this Yukawa matrix, then we can obtain different mass eigenstype. So some similar transforms of diagonals, such a matrix as a diagonalized matrix. There are some unitary matrix, and if such a unitary matrix acts on the such as private eigenstype, then the other will be some of the mass eigenstype will disappear. So the diagonalized matrix has the mass eigenvalues as diagonal element, and the such as unitary matrix acting on this private site will be yield at the mass eigenstype. That is some of the within sort of the Quark mixing. And yes, there are some of the binomials, some diagonalized matrix of the Yukawa's matrix and the mass eigenstype. And in this realistic Lagrangians as interaction forms, it contains some multiplications of the two unitary matrix field additions in there. So there are some of the Blyver change from the D type to the cakes in the charge recurrent by the expansion of W boson. And because the only such interactions occurs the Blyver's eigenstate, the propagation is the only considered the mass eigenstates as the latter shows the linear generations video. So there should be the some mixing matrix which is converted from the Blyver's eigenstate to the mass eigenstate, and it can be represented sort of by the multiplication of the two mixing matrix from the D-type cakes and the U-type cakes. And such a multiplication of the T-unitary mixing matrix can be defined as such a one unitary mixing matrix called the CK matrix for the Quark mixing, and it appears in the charged currents, such interaction terms in the Lagrangians. So that is the which aims through the Yukawa's couplings to give some Fermions mass by the couplings between the Fermions and the Higgs fields, and also I said about some Yukawa matrix, some diagonalization of the Yukawa matrix will give the Quark mixing, and that's a very similar formalisms of the neutrino oscillations. And maybe this next video, I will talk about how the neutrino record mass. The problems is it's a very small mass, and there are new interactions in the ions and SU2 get symmetries for the light and neutrino. But if we allow some minor neutrino, so that with the system mechanism, then the neutrino mass might be explained, and that is some of the not included in the standard model, so called beyond standard model to explain the neutrino mass. Maybe it will be discussed in the next time.